All right, this is the 1401 Unit 3 practice exam. We're going to work through this real quick. Let's look at the conceptual questions. All right, so which of the following bodies has the largest kinetic energy? Well, that's just a matter of looking at the equation, 1/2 mv squared. If you have mass 3 m and v, so the kinetic energy here is just 1/2 3m v squared. Okay, so in the second case, if mass 3m and speed 2v squared, well, that's a little bit different because k, I'll call this a, b, equals 1/2 3m 2v squared, or I'm sorry, this is going to be the whole thing squared because velocity is now 2v. So this is going to equal 2 squared is 4 times 3 is 12 times 1/2. Well, let's just say 12 times 1/2 mv squared, whereas this is 3 times 1/2 mv squared. Okay, so this is 3, 12. Let's look at option C, mass 2b and 3v squared. So Kc equals 1/2 2m times 3v squared, which is going to be 9 because you squared the 3. 9 times 2 is 18, so this is going to equal 18 times 1/2 mv squared. So this is 18. Mass m and speed 4v, so kd is equal to 1/2 m times 4v squared. So 4, that's 16, so kd equals 16 times 1/2 mv squared. And all four, of course, that's not true. So the only option is C, which is 18 times 1/2 mv squared. All right, so the weight of the object on the moon is 1/6 of its weight on Earth. The ratio of the kinetic energy of the body on Earth was moving with speed v to that of the same body moving with speed v on the moon is, we're looking at kinetic energy of a body on the Earth moving with speed v to that of the same body moving with speed v on the moon. Well, the ratio is 1:1 because kinetic energy only depends on velocity and mass. And if mass and velocity are the same, kinetic energy is the same on the moon or on the Earth. Potential energy would change because potential energy depends on the acceleration of gravity. Okay, so 3. An object with mass 1 kilogram is whirled in a horizontal circle of radius 1/2 meter with constant speed of 2 meters per second. The work done on the object during 1 revolution is, well, if you remember when we talked about circular motion, you have tension working on this body, and the displacement is always going to be perpendicular. So tension is perpendicular to any element dr of the displacement. So then, therefore, work equals 0. Because if the force is applied and it's perpendicular to displacement, then the work done by that force is 0. Okay, two bodies A and B have equal kinetic energies. The mass of A is 9 times that of B. The ratio of momentum of A to B is, well, they have equal kinetic energy, so kinetic energy A equals 1/2, well, say MA VA squared. Kinetic energy of B equals 1/2 MB VB squared, and we know the two are equal. So let's see, the mass of A is 3 is 9 times that of B, excuse me. So this equals 1/2 9 MB VA squared. And if this equals 1/2 MB VB squared, because the two are equal, so the 1/2s cancel, The MB's cancel, so you got 9VA squared equals VB squared. So we can say VB equals 3VA because I'll take the square root of each side. Okay, so the ratio of the momentum of A to B is momentum of A equals MAVA over momentum of B, MBVB. Well, we know VB equals 3VA. And we know MA is 9MB. So MB and VA cancel, and the ratio momentum of A to momentum of B is 9 over 3, so it's 3. 3 to 1. Wait. The ratio of momentum of A to momentum B. Okay, so 3 to 1. Yes. That was more of a math problem than a conceptual problem, but yeah. Sue me. All right. So the next one says that the force on a particle is given by some function. If the force acts from 0 to 2 seconds, the total impulse is, well, so where do you go to? Well, we're talking about impulse, so I can pull out my equation sheet. You remember the impulse is the integral of the force with respect to time. So it's looking for the total impulse from t equals 0 to t equals 2.0 seconds of f of t dt. So j equals the integral. I'm leaving out the limits of the integral just now for the sake of time. So 0.71 t plus 1.2 t squared dt. And if you remember, this is just basic rules of integration. If you have two terms, you can integrate them separately. And of course, you also know that you can pull out the constants. So now these are relatively simple integrals. The integral of t is t squared over 2. And that's evaluated from the limits of t equals 0 to t equals 2.0 seconds. Plus the second one, 1.2 times t to the third over 3. The integral of t squared is t cubed over 3. And of course that is also evaluated from t equals 0 to t equals 2.0 seconds. So the impulse then is t0 is nothing. That the whole term is going to be 0 at t equals 0. So it's 0.71 times 2.0 seconds squared. Well, I'll go ahead and evaluate it. Minus 0. So the first term evaluated from t equals 2 seconds to t equals 0, plus 1.2 times, oh, I'm sorry, this is over 2. The next term is 1.2 times 2.0 seconds cubed over 3 minus the same term evaluated at t equals 0, which is 0. So j equals, let's see, that's 4 seconds divided by 2 is 2, so that 2 times this is 1.42. Squared. I'm just going to leave off the units for now because there are going to be some complicated units involved here. So then plus 8 divided by 3, so that's 1/3. I need a calculator. 2 cubed over 8, that is 8 divided by 3 times 1.2, so that's 3.2 plus 1.42 equals 4.62 Newton seconds in the direction of F. And that's just because F is a vector. It's a one-dimensional vector from this equation here, but we know that J has to be in the direction of F because these are both vectors. The next problem. We have a roller coaster that starts from atop an 18-meter hill. It has a mass 2,000 kilograms, starts from 18 meters. It goes down one hill, comes up the other. So how fast is the car moving at the top of the 10-meter hill if friction is ignored? Okay. So in this case, all right, so where are we going to turn? Well, I would probably look at energy because the height is changing, so potential energy is changing. There's no collision, so that makes me think, why would I have to worry about the conservation of momentum? Momentum is not being transferred from one body to another. Or, I suppose you could look at it as the impulse. Well, there's no friction, so there's nothing removing energy from the system. So the problem also says use work energy considerations. So you don't even have to get confused over impulse and stuff. It tells you to use work energy. So in part A, if I start with the work of non-conservative forces equals change in energy, well, this is equal to 0 because the force of friction equals 0. So there are no non-conservative forces working on this system, so the change in energy equals 0. The only thing that's happening is we have potential energy at this point, which is converted into kinetic energy down here, and then it's partially converted back into potential up here. We don't even care about this part of the problem. We don't have to. As far as we're concerned, this cart comes down to this level and then continues on. We don't care that goes down and comes back up because it's just converting from potential to kinetic and then back to potential again. We might as well ignore that. So energy initial equals energy final. K initial plus U initial equals K final plus U final. We can say that this is Y final and up here is Y initial. The cart starts from rest, so K initial equals 0. If I want to expand that, I can say 1/2 mv initial squared plus mg using y equals 1/2 mv final squared plus mg y final, and v initial equals 0 because it starts from rest. Now, it has some potential energy at y initial. It has some kinetic energy here because it's converted part of that potential energy into kinetic energy. And it also has some potential at the energy because if we decide that this is the y equals 0 line down here, it's going to have some potential energy. So we are looking for the speed of the car, how fast. All right, so first of all, m's cancel from everything. So I'm going to start solving for final velocity. No, I'll write it like this. That's fine. Y initial minus y. Oh, wait. Yes, I wrote that wrong. Sorry. Okay, multiply everything by 2 and take the square root. So V final equals square root of 2g y initial. Now, is this positive or negative velocity? It's positive. Why? Because we're dealing with energy considerations, so it's not a vector, so we can't say anything about the direction of the velocity, so we're just always taking the absolute value. So square root 2 times 9.8 meters per second squared times y initial, 18 meters, minus y final, 10.0 meters. When you calculate all of that out, you have V final equals 12.5 meters per second. B, the car's brakes are deployed at the crest of the second hill, and you have the coefficient of friction between the wheels and the track. How far does it go? So it has some. We're going to redefine all our variables here into initial and final. So now this is the initial part, and this is the final part. Let's look back at the energy considerations. In this case, we do have the work from non-conservative forces. That work is friction. So the change in energy is E final minus E initial. E final is where the cart comes to a stop. So its kinetic energy is going to be 0 here. Its kinetic energy is not 0 here. Potential energy is going to stay the same, so it just subtracts out. I'll show you. So this equals K final plus U final minus K initial plus U initial. All right, equals 1/2 mv final squared plus mg y final minus 1/2 mv initial squared minus, I'm just distributing the negative sign, minus mg y final, because y is going to be the same, so these two subtract out. So it's not that the potential energy is 0, it's just that the potential energy doesn't change, so it subtracts out. We also note that V final is 0, so the work to non-conservative forces is just negative 1/2 V initial squared. Okay, at this point I solved the problem, but I had to go back and erase it because I dropped an M. So that mass is still there, 1/2 M V initial squared. And the V initial is V final from part A. So in order to get the distance that he skids, I'm going to have to go back to the definition of work. The integral of F dot dr. Well, the force of friction is constant because if you remember, remember the force applied over the force of friction, and they increase linearly until the object starts moving, then it drops down to a constant level. This is the force of kinetic friction. So the force of friction is constant, so I can pull it outside of the integral. And when in doubt, just assume that it's constant, because you'll know if I'm actually going to make you integrate something. So then the integral over dr is just F dot dr, which is just F dot, oh, I'm sorry, this is, once you integrate, that just becomes F dot delta r, which equals F delta r cosine phi. Now this is one-dimensional because it's just in the x direction, so we can say that's F delta x cosine of phi, where phi is the angle between the force of friction and the displacement x. I can actually write with the curly f down here. So we know that's the force of friction. Well, the movement, the displacement is in this direction, and the friction is in the opposite direction. So phi equals 180 degrees, and cosine of 180 degrees equals -1. So this is negative force of friction, delta x. And if I remember the other side of the equation, equals -1/2 mv initial squared. Notice they're just negative on each side, so the two cancel out. I can solve for the displacement now. Delta x equals, I'm just dropping the negative, mv initial squared over 2 times the force of friction. What is the force of friction? Well, that's equal to mass v initial squared over 2 mu k times the normal force. And it's a flat surface, so the normal force and the gravity work, and the sum of the forces in the y direction is Fn minus Fg equals may, which equals 0. So the normal force equals Fg equals mass times gravity. So I can say this equals mv initial squared over 2 mu k mg. M's cancel. So the distance that it skids is vi squared over 2 mu k g, which equals, and remember that v initial is v final from the first part, 12.5 meters per second squared over 2 times the coefficient of friction, which is 0.8 times the acceleration of gravity, 9.8 meters per second squared. And sorry, I'm running out of space here. Delta x equals 9.96 meters. Our next problem is a simple pendulum, a 2 kilogram mass. It's released from rest at x is shown, its speed at its lowest point. Okay, well this is work non-conservative equals change in energy. So what is the work from the non-conservative force? Let's see, if we consider tension, that's the only force other than gravity. Gravity is conservative. So the tension, the dot product between the tension and the displacement, is tension constant? Well, who cares? Because tension is always going to be perpendicular to any element of the displacement. So the work must equal 0. That equals the change in energy. So the initial energy equals the final energy. There's, by the way, I should go back and say there's no collision or anything here, so your mind should immediately go to energy conservation. So U initial plus K initial equals U final plus K final. It's released from rest, so that means, well, I'll just write it, mg so I'm just expanding kinetic and potential energy. Alright, so it's released from rest, so its initial velocity is 0. Now if I define the bottom here as 0, y final equals 0, y initial is right here, then I can also say that the potential energy at the end is equal to 0. Alright, so I have mg y initial equals 1/2 mv final squared. There's an m on each side, so those cancel out. So v final equals the square root, well, do I have to show? Okay, I'll show all the algebra steps. So g y initial equals 1/2 v final squared, so multiply each side by 2. 2g v initial, y initial, excuse me. equals v final squared, so v final equals the square root of 2gy initial. That equals the square root of 2 times 9.8 meters per second squared times y initial, which is 1.85 meters. And when you multiply that out, that gives you 6.02 meters per second. Alright, the next problem involves train cars that are coupled together by being bumped into one another. Alright, so there's a collision here. They're bumped into one another, so we're probably going to use impulse momentum theorem. Plus, we haven't done anything with impulse or momentum yet, so we probably are going to do so. So let's see. Suppose the two loaded cars are moving towards each other. The first has that mass and the second has some other mass, and they stick together. Okay, what is their final velocity? So I've got m1, m2, the I1, the I2. Then after the collision, the two stick together and they move with some velocity. This is m1 plus m2, where m1 equals 150,000 kilograms, m2 equals 110,000 kilograms, v1 initial equals 0.300 meters per second, v2 initial equals negative 0.120 meters per second. Alright, so if I start with the impulse momentum theorem, I first define my system as the two train cars. So I can say the impulse equals the change in momentum, which equals 0, because impulse is the integral of external forces over dt. So this equals 0, because there are no external forces going on here. All the forces experienced are between the two cars. So that means P initial equals P final, or M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. And we note because they stick together, V1 final equals V2 final, so we can just group them as M1 plus M2, and I'll call that V final. So that's defining that. All right. So what are we looking for? We are looking for what is their final velocity. So we're looking for VF. VF equals M1 V1 initial plus M2 V2 initial divided by M1 plus M2. V final then is just equal to, now I'm just inserting numbers, 50,000 kilograms times 0.30 meters per second plus 110,000 kilograms times negative 0.120 meters per second, all over 150,000 kilograms plus 110,000 kilograms. So the final velocity then is 0.122 meters per second. And thus concludes the practice exam.